Okay, we are live.
Okay. So we can start the presentation now, or should we wait for a few more people to join?
Yeah, whatever you prefer. We are all live, so you're welcome to get started if you'd like.
Okay. Just give 2 more minutes, and then I can get started after that.
Hello.
Hi, Marcus.
Hi, everyone.
Hi, Angelo. Okay, I think I can get started. So thanks everyone for joining this meetup. So in this meetup, we are going to cover the committer component in FabricX. So the source code is available under repository FabricX committer, and currently this is maintained by myself and Liron. So before going into the internals of committer component, so let's have a refresher on FabricX transaction flow. So we have clients and then endorser and then ordering service, and finally is the committer component. So the transaction would be initiated by the client, and they would submit the transaction to endorser to collect the endorsement. That is nothing but a signature, and the endorser can interact among themselves to endorse the transaction, and they can submit the transaction to the ordering service. Then the ordering service would order the transaction and then create a block, and that would be an input to the committer component. So the committer does validation and commit, and then once the commit is done, it will send notification back to both endorser and client depending on the use cases. So we have already covered endorser and then ordering service. So in this talk, we are going to only cover the committer component. So before going over committer in FabricX, it would be good to look into the committer in Fabric. So because most of the protocol we haven't changed, mainly we have changed the architecture. So it's good to have this background so that it would be easier to understand what we did in FabricX. So in Fabric, the endorsed transaction would be submitted to the ordering service. The transaction include reads and then writes, and also the signature without nothing but the endorsement from the endorsers. And then the ordering service would create a block, and that would be pulled by the organization peer. Currently, we have two organizations, and they would be pulling the blocks. So here block include transaction T1 and T2. Then the each peer has to run this block in 3 phases. So in the first phase, we have something called validation of signature against the endorsement policy. So each transaction would be modifying some of the data in the namespaces, right, managed by the chain code. So that have an endorsement policy that would dictate who need to sign the transaction to make modification to the namespace. So that is the first phase. And then the valid transaction would go through the read set validation. Basically, it would check whether any of the reads performed by the transaction have become stale. So in those cases, those transactions would become invalid. And then in phase 3, those changes would be applied to the database. The rights of valid transaction. So let's see what happens to transaction T1 and T2. Um, in phase 1, as I said, we would be validating the signature, right? So here, these validation happens in parallel. Suppose say it depends on the number of CPUs. that the hardware has. So we can process as many transactions as possible in parallel. And then once this stage is over, next we move to the validation of read set, right? Here, the transactions are processed serially because one transaction can impact the result of another, as we can see next. So let's say that the transaction T1 has read key A at version 0 and it is writing B. And let's look at the sample current state in the peer. So A is at version 0. So it means the read is not stale, right? So in that case, we would write the B with the version 2 because the earlier version is version 1 to the pending writes. So because we don't immediately write to it, that happens in phase 3. So then we take transaction 2 and it has read key B at version 1. But though the committed state is at version 1, we have a pending write, so which has incremented the version, right? So as a result, we have done a stale read. So the T2 would become invalid. So the write of C would not be added to the pending writes. So in the phase 3, only whatever that is available in the pending write would be added here and then applied to the database. So here you can notice that, so we are executing these phases in serial manner, right? For example, when phase 3 executes, phase 2 and phase 1 are like idle. And that applicable for all the other phases as well. So, I mean, from this itself, you can, kind of understand that, one of the key bottleneck in Fabric is the validation and commit. And here we are showing quantitatively as well. So this plot actually shows the time taken by committer to validate and commit a block of 150 transactions. So in the x-axis, we have elapsed time in milliseconds. And so these blocks shows the time taken by each of the phase and also some of the minor component in those phases. For example, the signature validation takes around like 16 milliseconds. Then we have read set validation and then the commit to the block store and then commit to state and history database. That takes the maximum of phase 3. And now assume that these phases are executed serially as well. So it's like a significant time taken to process a block. And so we can see, it overall takes around 63 milliseconds. So as a result, in 1 second, we can process 15 blocks, which translates to 2200 TPS. So that's what we get as a peak throughput in majority of the experiment as well. And this is also a best case scenario where the transaction is doing just a single read and then single write. Okay. So even, if we take a standalone draft, it could provide more than 6000 TPS, but this is the major bottleneck in Fabric that we have. Okay, so now we know the major bottleneck. So are there any effort in the past to improve the performance of Fabric? Yes, there were many. So as you all know, the first version of Fabric, that is v1.0, just provided only 100 TPS. And then the maintainers did a lot of effort to improve the performance from 100 to 2500 TPS. Then we continue to work and then try to improve the performance. And in some of the prototype, we could reach around 8000 TPS, but those optimization could not be merged to main Fabric because the changes were like very significant and very intrusive, and it will leads to a lot of backward incompatibility issue. At the same time, the academia also had multiple efforts. There are so many papers, more than 30-40 papers in this area. And one that stands out is Fast Fabric because they claimed 20,000 TPS. And when we benchmarked with the real workload, and we were able to get only till 4,000 TPS. So from this effort, it's very clear that the current Fabric cannot attain the CBDC scale, right? Because it requires more than 100,000 TPS. Like over 10x compared to what even some of the academia effort is claiming. So, so what is the reason for this? Why we are not able to attain more than 8,000 TPS or 4,000 TPS? What is the key thing? So we already saw that there are some bottlenecks, that is the validation and commit. But let's dive a little bit deeper so that we can understand what exactly we were doing wrong in Fabric. So the reasons are classified into two components. One is like compute and concurrency limit, and another category is data and storage constraint. So in the compute, the first one is there is a contention for CPU between the endorser and validator. So on the left-hand side, I have a fabric peer architecture. So we have endorser, validator, and committer. And the endorser and validator are like CPU intensive. So the endorser task is to sign the read and write set. So they provide the endorsement, right? So they have to cryptographically sign it. Similarly, the validator has to validate the signature against the policy. So both of them are CPU intensive and they are contending for CPU. So that is one of the bottleneck. The second thing is sequential validation. So as I already showed three phases, in phase two, where we validate the read set, so we had to validate each transaction serially because one transaction can impact the result of another. So this sequential validation also impacted the performance. And the third one in this category is non-pipelined commit. So as I said, the three phases, so they are executed serially. So when phase three is executed, phase one and two are like idle, right? So there is no pipelining between the phases. So that also makes performance very poor. And then in second category, we have reasons associated with the data and storage constraint. First one is state DB contention. So the endorser and committer both access database, whereas endorser mainly read and then committer mainly writes. So we don't have a sophisticated database in Fabric, right? We have level DB and then couch DB. They don't have comprehensive transaction semantics. So what we do is we kind of acquire an exclusive lock on the whole database. That means when the endorser is reading, committer cannot access the database. When the committer is writing data, the endorser cannot access the database. So that's kind of like a very naive approach, and that cannot help in scaling the performance for sure. And the second reason in this category is the storage bottleneck, because we are using standalone single node database. So whatever the IOPS and then the storage that we can get, that is the only thing that the peer can use. So that will again become bottleneck. And the finally is the transaction size. So there is a signature, right? There is a client signature, there is an endorser signature. Along with each signature, the X509 certificate is also sent. So each certificate is of size 1 KB. So this would increase the transaction size. As a result, both the network as well as the storage, the requirement increases. So from all these, and then based on our past effort, we have decided that to surpass 100K TPS, we have to re-architect Fabric. So not just optimize the existing code. So it must be re-architected. So that's the result of Fabric X that we have. And so how we re-architected, and what are the key ideas to achieve the scale that we want. So there are four key ideas that we had in mind to scale the committer. The first one is microservice architecture. So because in general, microservice architecture allow us to scale things horizontally by utilizing a lot of physical server. And the second one is parallel transaction processing, because as I said, in phase two, the validation of read set happens serially. So if we parallelize this, definitely we can see some improvement. And the third one is the pipelined phases. So currently the validation and then commit phases are executed serially. If we can pipeline them, then definitely we can process transaction quickly. And finally, the fourth idea is related to enhanced state management using distributed database, so that we can minimize the storage and IOPS constraint. So these are the four key ideas that we had. And let's go into each of them a little in depth. So in the microservice architecture, so the goal is to break this monolithic fabric peer. This is like a big peer, right? Into small services like endorser and then signature validator, validator committer, query service, so that we can scale each of them horizontally and to utilize as many server as we need to provide the performance that the application requires. And then the second one was with respect to parallel transaction processing. Here you can see in this figure that T1 and T2, they are like independent, and if they are independent, they can be executed in parallel. Whereas in T3 and T4, they are dependent on T1 and T2. So they have to wait for the execution of T1 and T2 to be executed. So now you can have a doubt that what these dependents mean. So these dependency is nothing but how they are, what values they are reading and writing. For example, if there are two transactions, T1 and T2, and if they are reading and writing completely different set of keys and values, then they are not conflicting with each other. They can be executed in parallel. Otherwise, for example, if they have read-write dependency or write-read and then write-write dependency between their read and write set, then we cannot execute them in parallel. We have to serialize it. Otherwise, I mean, we can have double spend or the serializability isolation would be violated. So this is the second idea that we can use to process transaction in parallel. And then the third is the pipelined execution of phases, right? So now we have dependency analysis. So that would give us the transaction that are independent. So with that, we would be able to execute these phases in parallel. For example, when phase 3 is applying changes for block n, at the same time, the phase 2 can validate reads present in transactions in block n+1. At the same time, for block n+2, the signature can be validated. So this would ensure that all the phases are active and even not just one block is processed. So even we can process multiple blocks at a time. So this would be enabled only because of the dependency analysis that we are doing, so that the independent transaction can go into these phases in parallel. Okay, this is our third idea. And then the fourth one was with respect to the enhanced state management. So here, so we had two ideas. One is deploy a distributed sharded database. So here the shard itself would be replicated, and then we would have a multiple database node, and they would be communicating with each other to commit the transactions and also to execute the queries. And another idea is to have, very traditional database like Postgres database, but with replication using primary and secondary architecture. But for this architecture to provide a very high performance, it is necessary to use a commercial flash storage system. So it's not a single SSD. So these flash storage would have an array of SSD, and they will have internal mechanism to provide very high IOPS. So with that, we would be able to achieve the performance requirement that we have, even with the traditional database by using PostgreSQL. So these are the four ideas that we had when we decided to scale the committer. And this is the final output. So on the left-hand side, we have the traditional fabric peer, and that has been re-architected shown in the right-hand side. The peer itself is divided into two services. One is endorser service, and then second one is committer service. The endorser service is already covered. So in the committer service, we basically have a component like sidecar, which would pull blocks from the ordering service. Then we have a component called coordinator, and then we have a bunch of signature verifier servers, and then we have a bunch of a read and write set validator as well as committer. Then we have a shots of distributed database node. Then we also have a query service that would be used by the endorser to query the ledger state. So let's go over a sample transaction flow so that it would be clear that how all these components are used to process a block. Let's say that the ARMA, that is our scalable ordering service, is emitting a block with transaction T1 and T2. First, it goes to the sidecar, and then sidecar store this data into a blockchain. So this is same as our block store in Fabric. It's append-only file system where we store the blocks. Then the coordinator would pull the blocks and then give it to the dependency graph. So here, so dependency graph would look into the read and write set of these transactions to construct the graph. So here, for simplicity, I have assumed that T1 and T2 are independent because they are reading A and writing A, and T2 is reading B and then writing B. So we have two nodes in the graph, but they don't have any dependencies. So the independent transaction can go to signature verifier manager. Then this manager would be splitting these transaction to the available signature validator. And here the T1 goes to one validator and then T2 goes to another validator. Then assume that they are valid. Then the transaction goes to the transaction distributor, who basically distribute the transaction to the available read set and then write set validator as well as the committer. So let's say T1 goes to one and then T2 goes to the another, we call it as a VC service. And what they do is they validate the reads, and if they are valid, they apply the writes. So that what happens in each of the read write set validator and committer. So the post, the commit, there is a reverse path as well, which is not covered in the slide, which basically sends the transaction status and all the way to sidecar, and then sidecar sends the notification to the client, and then as well as the endorser. So this is the complete commit flow in FabricX. So is there any question so far on the architecture or what we proposed or what we have done? Okay. Okay, so if there are no questions, I will cover some of the 4 key challenges that we faced while developing this committer X component. So the first challenge was related to microservice decomposition. So now we have the monolithic fabric peer. So we need to decide that how we are going to split into small services such that they are not becoming like a chatty service, but they are interacting only for necessary things. And for that, we really couldn't use many of the legacy code that is there in Fabric repository because those codes were very tightly coupled to the monolithic architecture. So we had to write this the committer from scratch. So this was quite a challenging task. And then the second one was with respect to resiliency. So earlier we had just a single Fabric peer per organization, right? Or we could have 2 or more peer as well. But now we have split the single peer into more than 6 services. So now the failure and recovery would become more complex because any of the services can fail or any of the network links can fail. So the network link failure can be transient, like few milliseconds, or it could be prolonged as well. So all the scenarios has to be taken into account. Like if the sidecar fails, what are the impact? If coordinator fails, what are the impact? And it could be a transient failure or permanent failure. So all those cases had to be considered, and then the solution has to be implemented. It was very challenging and then fun thing to do. And we have successfully done it. Now we have a lot of unit tests and integration tests covering all the failure scenarios. And then the third challenge was with respect to graph management. So, I mean, our goal is to provide more than 100,000 TPS, right? So in that sense that the dependency graph at any given time, it should be able to handle more than 500, almost 500,000 nodes. So this was very quite challenging because we need to devise a data structure that can handle these much amount of nodes. And at the same time, when we have, a graph with this many number of nodes, the hundreds of thousands of transactions would be arriving into the coordinator. So we need to look into those transactions, look at its read set, write set, and then find the dependency, and then add those transactions to the dependency graph. So that was very quite challenging to achieve it. It took quite some time. And currently, this dependency graph is able to provide almost 200,000 TPS per second. And currently, this is also one of the bottleneck that we have. As a result, we couldn't go like millions TPS per second for the committer. So we are continuing to work on it and then improve it further. And then the final challenge was with respect to the database usage itself. So in the initial prototype, we were not getting good throughput. It was some tens of thousands of TPS. And the main bottleneck was the validation and commit latency. So because many of the validation we were doing at the application layer, that was making things very slow. So what we decided was that, we can consider the happy path and then optimize for the happy path. So as a result, we divided the validation into two steps. Some validation happened within the database itself using stored procedure, and something would happen at the application logic. So this would this helped us to remove the bottleneck that we had with the database. Okay, so let's comes to the performance of committer. Let's look into the server configuration that we used. We definitely use some powerful machines, 48 cores, 64 GB RAM, and then 1 TB SSD and 10 Gbps network bandwidth between the servers. And the committer itself was deployed using 14 servers, one for the sidecar, one for the coordinator, and then signature verifier took 3. And then validator committer took 3 servers, and then database node were 9. And note that the validator committer was co-located with the database nodes because they are the one that talks more with the database, right? So we kind of co-located them. And so in the graph, you can see in the x-axis is the number of input and output per transaction. That is nothing but the number of reads and writes. And then in Y1 axis, we have throughput, and then in Y2 axis, we have the latency. And the latency was always below 1 second, whereas throughput, decreased from around 230 TPS to almost like 90 TPS as we increased the number of reads and writes. So this was expected because with the increase in the number of reads and writes, the dependency graph has to do more work, because it has to process a lot of reads and writes, right, to detect the dependency. And also the validation that the database does. So there is an increased latency there as well. So as a result, the throughput was going down. But however, compared to Fabric, we were able to get a 100x improvement in performance. That was significant. And as I said, our system is built with a lot of resiliency, right? So here in this experiment, what we are doing is now we are killing the VC service one by one. So we have 3 VC service. We kill 1, 2, and then 3. And then we show that when we are restarting them, the system would stabilize very quickly. So in the x-axis, we have the time lapse, and then y-axis is throughput, and then y2 axis is the latency. So the pink plot is the total throughput of the whole committer. And then we have a black, red, and then green one, right? Those are the throughput provided by the individual, the validator and committer service. So at the 48 second, we are killing the VC service 1. So as a result, the existing 2 VC service, they are accommodating the load. As a result, the total throughput is not coming down. So the failure is, it doesn't impact the performance here. Then at the 100 second, we are killing the VC service 2, but then we have only 1 VC service. So the total throughput is equivalent to the throughput of the remaining 1 VC service. Obviously here we dropped the throughput, right? Because now we have only 1 VC service. Then we killed the VC service 3 as well. Then the throughput becomes like almost 0. Then we are bringing in the VC service 2. And as soon as we bring in the VC service 2, you can see that there is a significant the growth in the total throughput. It goes till 250K TPS. The main reason is that when the all VC service are like dead, there is a lot of queuing up happening at the coordinator and then signature validator, etc. So as soon as it comes up, there is a lot of uh, the requests that are pending, so that it could process them very quickly. So as a result, we can see there is a spike. But after that, once the spike, once we start the other VC services, then it stabilizes and then go back to the old 200 kTps. So this shows that our system is very resilient and any node can fail. So this plot shows for VC service, but we can kill the same way for signature validator or any of the database node, coordinator, sidecar. Anything can be killed and the system would continue to work. And then we need to look into the cost as well, right? Though we are giving 100x improvement over Fabric, so definitely we are using 14 servers, and there is also resource utilization associated with it. So here we take the following resource metrics: CPU, memory, disk, network send, and then network receive. And then we have coordinator, signature verifier, and then VC service plus database node. They are co-located. So the VC service and database node consume the most CPU, memory, and disk, mainly because of the database, not the VC service. And then for network, I mean the 1.7 Gbps send and 1.2 Gbps receive is done by the coordinator, because the coordinator is like a heart, right? It communicates with all the other components. So there is a lot of communication with all the other components. So the network utilization is high. So though we have used 14 servers of 48 cores, but I mean, if we need to do an optimal resource allocation, we definitely don't need to provide powerful servers to all the services, and then also powerful network bandwidth to all of them. So we can do a lot of optimization to reduce the cost as well. So for any questions on the performance numbers or experiment results, setups? Okay, I will move on to the future work. So the future work that we plan to do is with respect to data consistency check. So currently, the limitation that we have is like, suppose say there is a fork in the network due to a bug, or any of the malicious admin has modified data in the database. So that needs to be detected, right? So in Fabric, we have something called a snapshot. And so using the state snapshot, I mean, two organizations can compare the result to find out any divergence in the state. So we would like to provide a similar feature in Fabric X as well, because that would also help to, I mean, speed up the onboarding process, because you don't need to process all the blocks to onboard a new organization. So however, here it's not as straightforward as we done in Fabric, because in Fabric it's a single process. Here we have 6+ services, right? And also one of the good thing is that we have a distributed database which are sophisticated, and they can also provide a lot of APIs to take the snapshot, etc. So we need to evaluate the features available in database, and then try to automate this whole snapshotting, as well as there should be a consensus on the snapshot as well, which is not available in Fabric. So those are the things that we are planning to do as part of the future work. And then in the second future work, that was with respect to block store. So you might have seen that the sidecar is the one that is managing the block store, right? And sidecar is like a single entity. And so if there is any crash, or if the hard disk corruption happens, then the ledger would be kind of lost. And also we provide many ledger APIs to, for example, get block by number, get transaction by ID, all those things. And so because it's a single node, I mean, there could be a performance bottleneck on those nodes. So that's why we would like to work on a solution where the block store itself is kind of distributed, so that even the writes and then queries, all those things can be provided at a high scale. Further, we can enable historical queries and any kind of warehouse analytics query on top of this the distributed block store. And also we are planning to provide a notification service on top of this block store as well, so in which the user can register, for example, when a particular key in a particular namespace is changed, then notify me. So all these features would be part of this scalable block store. Yeah, so that's the end of my presentation. Thank you all for listening. And if you have any questions, you can ask now. So do you have any questions, or everything was clear and no doubts? Okay. So are there any questions on the chat, which I'm not looking at?
Yeah, I'm not seeing any questions on the YouTube or LinkedIn live streams as well. So I think it was just a very well-informed presentation.
Okay, so if you don't have any questions, I would stop sharing the slides.
Oh, great. If there are no other questions, I'm happy to end a little bit early. Great. Thanks everyone for your time. And thank you again for presenting. Great presentation.
Yeah, thank you for
Thank you.